The picture that started all of this does not look like much at first glance. It is a simple frame from the rover on Mars, the kind of raw photo that usually gets posted by the hundreds, dusty and quiet. With the horizon in the lower part of the shot and a pale sky above. But tucked into that sky is a small mark, hardly bigger than a few pixels, and the color looks wrong. It is not the soft brown of a dusty Martian afternoon or the butterscotch haze you expect. It is a faint blue smudge, like a thumbprint brushed across the air. That little blur is what brought us here. It did not arrive through an official feed with a caption and a serial number. It showed up on a scientist's personal blog with a note that said, "More or less, look closely at the upper right." In a week when official channels were quiet, that one line felt louder than usual. If you have ever looked through the rover's raw image pages, you know they are not built for drama. They are working files, posted in batches. Some are bright, some are underexposed, some are test shots. Navcams and Mastcams aim and click. And the files carry long names that tell engineers which camera took which frame on which sole. Most people scroll past them until a polished version appears later with a clear subject. This time, people stopped because of the color. A blue mark in a sky that is usually tan makes the eye pause. It raises a simple question that matters a lot. Did the rover capture the interstellar object people have been talking about? Or are we staring at a camera quirk that fooled us for a moment? To answer that honestly, we have to slow down and take the picture apart. First, think about how a rover camera sees the world. The sensors are very good, but they are built for work on the ground, not for deep sky photography. Short exposures are common, so moving parts stay sharp and the robot can drive safely. Long sky exposures are rare. The data is often compressed before it is sent home to save bandwidth. The color you see is not always the color the sensor saw. Software reconstructs a color image from a pattern of tiny red, green, and blue filters over the pixels. All of those steps can create little surprises, especially in areas with very little detail, like an empty sky. A bright dot can smear a little. A weak signal can shift a shade. A compression block can leave a faint edge that looks like a shape. Now think about Mars itself. The Martian sky changes color in a way that seems backwards to our Earth eyes. During some times of day, dust in the air scatters red light and lets more blue light through near the sun. That is why photos of a Martian sunset can look blue. The dust content, the sun angle, and the amount of haze above the rover all change how the sky looks. If a tiny bright object passes through that sky and the camera takes a quick exposure, the result can land in a strange place. It can be a little patch of blue in a tan field, even if the thing out there is not actually blue. The sensor and the air work together to paint it that way. This is not to say a smudge means nothing. It means we have to test it like a detective would. The first check is time. The frame should have a moment attached to it. Even if the post was informal, the original file, if real, has a timestamp. Does that time match any prediction for when 3i Atlas would have crossed that patch of sky from the rover's location? A basic sky chart can tell us where a line through Mars' sky would place a fast mover at that minute. If the shot is pointed in the wrong direction or the sun angle makes it impossible, the smudge looks less interesting. The second check is neighbors. Raw rover images are rarely taken alone. There is often a pair or a short sequence. If there is a left camera and a right camera, we can ask a simple question. Does the mark appear in both? If it appears in the left frame but not the right frame taken at the same time, it might be a sensor hit. If it appears in both, in the right place with the right offset between lenses, it becomes more promising. If there are 3 frames in a row pointing at the same place, does the smudge move the way a point in the sky would move over a few seconds? If it is stuck to the same pixels even as the rover shakes a little or the camera jitters, it might be dust on the lens or a fixed hot pixel. If it walks a bit between frames while the ground stays put, it acts like a real object. The third check is shape. Cosmic rays strike sensors now and then and leave bright, sharp, thin marks. They are usually white, often only a pixel or two wide, and they tend to be crisp. A lens flare is a soft, round, semi-transparent spot, often lined up with the sun and the center of the frame. A dust mote near the sensor makes a soft donut shape if the lens is focused far away. The blue smudge in this case looks like a tiny feathered oval. That does not prove anything, but it moves it away from some of the common artifacts. If we can get to the raw color channels, we can check whether the blue channel is heavy and the red and green are light, or whether compression gave the blue pixels a false boost. A single frame will not let us finish the job, but it can tell us whether the question is worth more time. The fourth check is brightness. Even a very fast object has to be bright enough to be seen by a rover camera with a short exposure and a broad daylight sky. If a rough prediction says the object would be extremely faint at that distance and speed, we would not expect a clear hit. If the prediction says it could be bright for a moment due to an active patch puffing gas toward the sun, a short, faint blur could be reasonable. People who measure such things often talk in magnitudes, which can feel abstract. In simple terms, we can compare the smudge to known stars in the frame if any are visible, or we can compare it to noise in the sky. If it is only as strong as the noise, it is likely nothing. If it stands above the noise in a way a star or a planet would, it earns another minute of attention. There is also the matter of the files road home. A raw rover image that is real will match the way NASA names files and stores them. The name often includes camera codes and a sol count. The blog post that drew eyes to the smudge did not bring a formal caption, but a careful reader will look for a link back to an official archive or to a mirror that copies those archives with the same names. If it does not exist anywhere except that blog, we can still look, but we have to hold it lightly until we find it on a server that is known and stable. During a shutdown, the press office may be silent, but the raw servers often still update because they are part of the normal pipeline. Quiet does not always mean no new files. It can mean no write-ups. If the file shows up in the formal place later with the same pixels, the confidence grows. We also have to talk about color in one more way. Earlier chatter about this interstellar object used the word green because some reports described glowing fissures in space-based images. If those reports were based on long exposures with filters that favor certain wavelengths, they are not the same kind of look as a quick daytime shot on Mars. Blue on Mars could be a scatter effect or a white balance quirk. It could be the camera pulling clean detail in the blue channel where the sky is a little darker. It could be a real physical color if the object has a plume that shines in a band. The rover's blue pixels pick up more than red or green. A single frame cannot tell us which, but it can remind us not to expect the same. Paintbox from two very different cameras under two very different skies. Another quiet check is the background. If the smudge sits over a known star and the star does not show in the frame, that is odd. If the smudge sits in a patch of sky with no bright stars at that time and date, that is normal. Simple phone sky apps can help here. Set the location to Jezero Crater, set the time to the claimed moment, and look at the patch of sky the camera faced. The wrong star pattern under the smudge is a fast way to doubt. The right emptiness is not proof, but it is not a mark against it. The last check for now is harmony. Does the story the pixels tell match the story the clock tells, the story the rover tells, and the story the sky tells? A clean case is boring on paper. The time lines up. The direction lines up. The mark behaves like a small, faint thing in a bright sky. It repeats across two eyes or across two frames. It looks the same in the raw channels with no strange edges from compression. It sits in a file that follows the rules and comes from the place it should come from. Each piece on its own is not enough. Together, they make a shape we can trust more than a feeling or a headline. Even after all of that, we do not declare anything. We step back and remember the scale of the claim. A point of light on a rover photo is never on its own the final word about an interstellar visitor. It might be the first nudge that tells everyone where to look next. It might be a small, honest mistake that taught us something about how a camera and a dusty sky can trick the eye. It might be the opening paragraph in a longer report that will need the help of Earth-based telescopes, Mars-based orbiters, and the hard math that turns points into paths, and paths into orbits, and orbits into a clear answer about what passed through that sky and whether it came to us from very far away or only from the inside of a sensor that was doing its best in a hard place on a quiet day when the internet wanted a louder story than the pixels alone could carry. When people hear the word shutdown, they often imagine a big switch flipping off, buildings going dark, and everyone being sent home at the same time. That picture is simple, but it is not how space work actually runs. A government shutdown changes who is allowed to work in public, not whether spacecraft keep flying. The law says most public-facing work has to pause until funding is approved. Press releases, live streams, social posts, classroom outreach, and media interviews are put on hold. At the same time, the law also says work that protects life and property can continue. That is where space missions live. Keeping a spacecraft healthy, pointing a radio dish, and moving data safely are all part of essential operations. So the public voice goes quiet. But the hands that keep the machines alive stay on duty. Inside the teams, there is a clear split between roles. Public affairs, social media, web editors, and many scientists who are not on the current shift are furloughed. They are told not to work, even as volunteers. That rule matters because it protects both the people and the program. On the other side are flight controllers, power and thermal engineers, navigators, deep space network schedulers, and mission operations leads. They're accepted, which means they keep working. Their checklists do not depend on news cycles. They follow long plans that were written and reviewed weeks in advance. The rover still needs heat through a cold Martian night. A probe still needs to roll to keep its batteries within range. A radio still needs to lock onto a carrier at the right minute when Earth rises over a distant horizon. Those steps are not optional. They are the reason the mission exists. Think of it like a hospital after visiting hours. The front desk is dark. The gift shop is closed. The public hallway is quiet. But behind a set of double doors, the operating room is bright, monitors are on, and staff move with steady focus. Space work during a shutdown looks the same. You see the dark lobby because that is the part you normally walk through. You do not see the back rooms, but they are the whole reason the building stands. A paused press page is the lobby. The back rooms are the control centers, the cooling loops, the software that checks a voltage and sends an alert if it drifts, and the people who answer that alert at 3 in the morning, the deep space. Network is a good example of why silence online does not mean silence in space. The DSN is 3 large complexes of radio antennas in California, Spain, and Australia. They take turns talking to spacecraft as Earth spins. Their schedules are written like train timetables. A mission gets a block of time to downlink data. Another gets a block to uplink commands. The blocks hand off from one complex to the next, so a signal can be heard for many hours. Those blocks do not vanish because a press office is closed. Operators still aim dishes, lock signals, and move data along paths that were booked days ago. If a storm passes over Madrid, Canberra picks up a little more time. If maintenance takes one dish down, another dish steps in. To someone refreshing a website, the day looks empty. On the ground, it is a calm, busy relay that does not care about headlines. The same is true for the commands that drive a mission. Most deep space craft do not wait for same-day instructions. Teams prepare sequences, which are bundles of commands that tell a spacecraft what to do for many hours or even days. A sequence might say when to turn on a heater, when to rotate a wheel, when to take an image, and when to point an antenna home. Those sequences are tested on simulators and reviewed by several sets of eyes. They are uploaded during scheduled contacts and then run on the spacecraft at the appointed time. If anything looks strange, the craft can enter safe mode, a protective state that points the radio to Earth and stops non-essential activity. Safe mode is common sense written in code. It is not a secret and it is not dramatic. It is there so the machine can wait quietly for help, and there are always people listening for that call, shutdown or not. Data handling follows the same pattern. When a rover snaps a picture or an orbiter finishes a pass over a target, the raw data is stored and then sent during the next DSN contact. Back on Earth, the bits move from a ground station to mission servers. Engineers run quick health checks to make sure the data is not corrupted. Later, deeper processing polishes the files for long-term archives. Those archives, like the Planetary Data System or the European Planetary Science Archive, are formal libraries. They are not social media. They do not run on daily captions or clever headlines. They accept files with product IDs, times, and instrument names. During a shutdown, the people who would write a friendly blog post or a tweet are off duty. But the pipeline that catches and shelves the data can still operate because it falls under mission continuity. That is why a mission can be quiet on the surface and still be building a stack of files to share as soon as the front door opens again. There are edge cases, and they are managed with care. If a message is needed to protect public safety, it can be cleared and sent. If a mission status has to be shared with international partners to keep a joint activity safe, that happens through established channels. If a contractor runs a system under a different funding stream, their part may continue even if a federal team is paused. These are not tricks. They are guardrails. They exist so that safety and stewardship come first. It also means some pages you are used to checking may update, while others sit still, which adds to the sense of uneven quiet. The important point is this: uneven is normal during a pause. It does not mean someone is hiding a thing that day. It means people are following rules that tell them exactly what they can and cannot do until funding clears. For the public, the most visible change is the loss of little signals. On a normal day, those small posts are like a heartbeat. A short video clip of a test, a snapshot of a horizon, a chart with a few dots and a sentence about what comes next. When those stop, our minds notice. We start to listen harder. We are built to fill gaps. That is when rumors get louder, because they offer a quick story that fills the empty space left by a missing caption. It helps to remember that the story you can trust usually lives somewhere less exciting. It lives in a DSN schedule that shows who is talking to which dish at what hour. It lives in an operations log that says a heater came on at 2:14 UTC and turned off at 3 o'clock. It lives in a file tree where a directory fills with new image IDs that will become public as soon as the people who post them are allowed back at their desks. It is also worth noting that science culture itself is slower than social media. Even without a shutdown, a good result usually waits for checks by a colleague, a look from another telescope, or a second instrument on the same craft. That delay is not a stall. It is the work. During a shutdown, that careful rhythm and the rules about public work overlap. The result is quiet for a while, followed by a catch-up period when the pause ends. You sometimes see a data dump day soon after funding returns, when lots of small updates land at once. It is not a conspiracy. It is paperwork meeting patience. If you have ever run a small business, the pattern may feel familiar. You can close the front office for a week and still keep the machines in the back running, the inventory safe, and the schedules on track. When you open the door again, you put the receipts in order and you tell your customers what you did while the sign was turned around. Space is like that, just on a scale that reaches out millions of miles. The main difference is that space cannot wait for us. Orbits keep moving. Light time keeps changing. Antennas must pivot when geometry says it is time. Those are the clock's mission operations follow. Shutdown or not, they make their marks, they turn when the math says to turn. And the people who watch those marks keep showing up because the job is built that way and has been for a very long time. When people write 3I, they are pointing to a very specific idea. The letter I means interstellar. It is a badge we only use when an object passing through our solar system is not bound to the sun. We did not have this badge until a few years ago. In 2017, a small, fast object cut through the inner system on a path we had never seen before. It did not circle back like a comet or an asteroid. It moved on an open curve, gained its own special label, and earned a Hawaiian name that fit the moment, Aumumua. The Scout, 1I 2 years later, in 2019. A true comet from beyond our neighborhood appeared, with a fuzzy coma and tail, and took its own place in the list, as to I, Borisov. Those two events changed the way we look up. They prove that the space between stars throws travelers our way, and that our surveys are now sharp enough to catch at least a few of them as they rush by. Oumuamua was strange because it broke the rules we were used to. It was faint. It brightened and faded in a pattern that fit a long, thin body or a wide, flat one, depending on how you read the light. And it did not show a normal comet coma, even when it passed close to the sun. More surprising, it felt a tiny push that could not be explained by gravity alone. The best calm guess is that sunlight pressure or a very gentle outgassing acted on a big surface area or very light structure. People argued about its shape because the light curve allowed more than one answer. The two simple pictures a cigar versus a pancake were only stand-ins. For the math, that said the object had strong variations in brightness as it spun. We learned a lot from it, but we also learned how much we don't know when we only get a few weeks with a dim, fast target. Borisov, on the other hand, felt familiar in a soothing way. It behaved like a comet should. It had gas and dust, it formed a tail, and its chemistry looked a lot like comets born in our own cloud, with some interesting differences in dust grains and carbon monoxide. That second visitor told us interstellar space can deliver the kinds of bodies we already understand. It's not only the strange, quiet ones. Between the two, we now have a first chapter and a second chapter in a new book. A third entry 3I would start to tell us whether Oumuamua or Borisov is more typical, or whether the interstellar population is as diverse as the objects we see at home. To earn the eye, an object has to meet a clear bar that does not care about headlines. Its path around the sun must be open, not closed. The math for that is simple to say and hard to measure. Astronomers fit an orbit to a string of positions on the sky. Each position is a time and a spot against the stars, measured by more than one telescope over more than one night. When the fit is tight, they look at a number called eccentricity. If that number is less than 1, the path is a closed oval. If it is greater than 1 by a comfortable margin and the error bars are small, the path is open hyperbolic hand. The object is just passing through. You also look at the speed far from the sun, the so-called speed at infinity. If that remains above the sun's escape speed even before the object falls inward, the interstellar case gets strong. This is what we mean by open orbit math. It is not a mood or a clip. It is a repeatable fit posted in public, where anyone can check it. The paper trail for real discoveries is also part of what 3I would mean. New objects start life on the Minor Planet Center's confirmation page. where sky surveys post candidates and other observers help confirm them. If a target holds up, it gets a provisional designation. As more positions come in, the orbit improves. JPL posts a small body page with the best fit so far and the uncertainties. If the path stays hyperbolic and the measurements are solid, the Committee on Small Body Nomenclature assigns the next I number. Only then does the shorthand 3I belong to the object. After that, it can get a name the way the first two did. Chosen by the discoverer with rules that honor places, people, and language with care. This is where rumors and reality often part ways. A single detection is not enough. A single pretty image is not enough. You need several nights, different longitudes, and more than one telescope. You need agreement. You need to see the dot move how and where the math predicts, not just once, but again. If there is talk of a view from Mars and one from Earth, that is powerful because the two viewpoints give a wide baseline for triangulation. Parallax between Earth and Mars could lock down the distance faster and make the orbit fit, tighten in days instead of weeks. But even that needs clean times, known pointing, and a match between what the rover or orbiter saw and what ground telescope saw. Without those pieces, 3I is just a label people type because they want it to be true. If 3I is confirmed, what would it give us beyond pride in catching another traveler? It would let us compare 3 stories. One story would be about objects that are quiet and solid, with unusual shapes and subtle non-gravitational pushes. Another would be about proper comets with gas, dust, and classic tails. A third could be something in between, a weakly active body that surprises us in one band but not another. With 3, we can start to ask about common chemistry. Do these visitors carry more nickel in their dust, more carbon monoxide in their gas, or less water than we expect? Do their colors suggest surfaces baked by long exposure to cosmic rays in deep space? Do any of them break up easily, or do they stay intact? The statistics are still tiny, but every new point changes the curve. There is also the bigger question of direction. With 2 interstellar visitors, people have already tried to trace their incoming paths back into the sky to see if they share a source region. The results are suggestive but not firm because small errors turn into large angles over light years. A third incoming direction could test whether there is any clustering, or whether we are sampling random debris from many birthplaces. If multiple visitors arrive with low inclinations close to the plane of the solar system, that could tell us something about how interstellar objects drift and settle as they wander between stars. If they come from all over the sky, it tells a different story about chaos and long time scales. For a general audience, the confirmation bar is easiest to picture as a checklist. Do we have a posted orbit with eccentricity above 1? And is that true when we include more nights? Do independent teams agree on the fit? Does the speed make sense for an interstellar origin before solar heating changes the behavior? If there are claims of non-gravitational acceleration, are they small and consistent with light pressure or gas jets? And are they measured by more than one group? If there are claims about composition, did they come from spectra with real calibration, not from color impressions in compressed images? If a rover or orbiter is part of the story, do the raw files live in formal archives with the right timestamps and product IDs? If these boxes fill in, 3I is not just a hope. It is a record. It is also fair to admit what we might not get even with a confirmed 3I. We may not know its exact shape. We may never see more than a point of light in any individual frame. We may not catch gas jets directly. We may have to infer properties from how the light brightens and dims as it spins, and from how the path bends near the sun and the planets. That is okay. Oumuamua taught us how much an honest light curve can tell us when images are small. Borsov taught us how much a good spectrum can tell us even with a simple coma. Each visitor shows us what tools matter most for a fast encounter and where we need to build better ones. What makes 3I historic? Beyond the number is that it would be the first time we could plan a response with experience. When Amumu arrived, we were surprised. When Borsov arrived, we were quicker. Now sky surveys are wider, software is faster, and astronomers know the playbook. If a third visitor appears, telescopes will be pointed sooner, and instruments will be chosen with lessons learned. If there is even a chance of an Earth-Mars parallax, teams could coordinate to lock the range and speed. If spacecraft can stare at the right patch of sky without risk, they might try. If not, Earth will still be ready with eyes that have practiced this exact drill. So, when you see 3I online, let it mean what it truly means. It is not a feeling. It is not a dramatic caption. It is a promise that a string of positions on the sky has been turned into a path that cannot close. A path posted by people who put their names on their measurements. A path that stands when checked by others. And a number assigned by a body that moves slower than the news on purpose. Because that pace is how you trade excitement for certainty in a field, where one pixel can be the whole story or no story at all. And the difference is in the math, the dates, and the steady hands that do the fitting while the object keeps moving on its way out, leaving us with one more line to add to a short list that is already changing. How we think about the space between the stars and what drifts in it. When people say Atlas in this story, they are not talking about a myth or a map. They mean a real sky survey that watches for fast movers every clear night. The full name is Asteroid Terrestrial Pact Last Alert System. It is built to find small objects racing through the sky that could pass close to Earth with little warning. To do that, the team uses wide-field telescopes that scan huge slices of the sky again and again, taking short exposures that freeze motion and limit blur. Software compares fresh images to a recent reference, subtracts the background stars, and flags anything that seems to move or brighten in a way a fixed star should not. Most of those flags are junk cosmic ray hits, airplane flashes, satellites, camera noise. Filters knock down the noise. What survives goes to a human who looks at a simple cutout and says yes or no. When the answer is yes, the survey ships the positions to the minor planet center so other observers can help confirm the find. The hardware is not giant, but it is fast and persistent. The telescopes have very wide fields, which means a single frame covers a big part of the sky. That is the point. Atlas wins by watching a lot, not by going very deep. A few more telescopes were added over the years, giving the network better coverage across time zones and seasons. On a good night, the system can scan most of the visible sky several times. The short exposures help Atlas catch objects that streak slightly in a single frame. The software looks for that streak and checks that the streak moves in the same direction over several frames. Those little sets of positions are called tracklets. A tracklet is the first building block of a real orbit. If Atlas helped spot our rumored object early, that would make sense. A visitor from outside the solar system tends to move fast across the sky. It can have unusual motion compared to the slow drift of most main belt asteroids. It can look like a faint, short streak when the exposure time is just right. Atlas is built to highlight exactly those things. But the survey flag is only the beginning. What matters next is the trail through official places. The Minor Planet Center runs the clearinghouse for measurements. A candidate appears on the Near-Earth Object Confirmation page with a code and a few early positions. Other telescopes turn toward that patch of sky. They take their own images and send their positions to the MPC. After a few hours, you can see a little list forming observer codes, times, right ascension and declination, brightness. With enough positions over more than one night, the MPC can publish a minor planet electronic circular. That is the first sign that the community agrees something real is there. Once the positions stack up, orbit computers get to work. The JPL Small Body Database posts a page with the best fit orbit and an uncertainty estimate. Early in a discovery, that page is wobbly. The arc length might be a day or two. The number of observations is small. The uncertainty is large. As more observers add data, the fit tightens, the arc length grows, and the hyperbolic or elliptical nature of the path becomes clear. For an interstellar object, the eccentricity climbs above 1 and stays there even when you include more data. If all that holds, the Committee on Small Body Nomenclature assigns the interstellar badge, the I, and the next number. Only then does the nickname people have been using on social media line up with a real designation in the book. It is common to see the word ATLAS attached to a comet name in parentheses, like Cisegan Arling Arliemsen, Atlas. That credit tells you who first reported a workable detection or who shared early discovery credit. You might be tempted to think 3I Atlas would be the official name for a third interstellar visitor. But that is not how the interstellar label usually looks. Oumuamua is 1I. Oumuamua. Borisov is 2I Borisov. The discoverer credit shows up in the discovery circulars. And sometimes the name itself honors a person or a place rather than a project. Atlas could still be the credited discoverer, and the shorthand used online might be fair as a placeholder. It is just not the final form until the committees say so and the orbit. Numbers match the claim. If you want to check whether Atlas really touched the story, you can look for a few signs that do not depend on a press post. First, you look for a candidate line on the MPC's confirmation page with observations, attributed to the observatory codes that belong to the Atlas stations. Those codes are public, and the MPC assigns them. Second, you check whether follow-up observers began reporting within hours, because that is the normal rhythm for an active NEO pipeline. Third, you watch for a minor planet electronic circular or an observational update that cites the survey and lists other contributors. Before the I label is ever assigned, you should see that paperwork trail. Without it, Atlas saw it first is just a sentence someone typed, . All of this can feel slow if you are used to the pace of a social feed. But Skywork is built to trade speed for confidence. A survey like Atlas is a net. It scoops up candidates and throws them into a shared bucket. The Minor Planet Center is the dock where everyone dumps their catch. The community sorts the fish from the gloves and the rope and the seaweed. Not every night yields a prize. Not every alert becomes a named object. But when something strange appears to odd motion, the fast apparent speed, the hyperbolic hint process adapts. And observers all over the world lean in at once. It is also important to understand what Atlas does not do. It does not set the final orbit by itself. It does not assign names. It does not write the official story. It starts the story and keeps scanning while others confirm. Many times a second survey will share the discovery credit because two groups saw the same object within minutes of each other. That is common with comets, where you might see a shared name like Sukunchinlatlas. For an interstellar candidate, the sharing would look similar. The MPC circular would show who contributed early tracklets, and the I label would come later when the orbit is clear enough to stand on its own feet, because the survey covers so much sky so often. It sees many things that are not new objects at all, satellites flaring, planes, glints, even bright stars that confuse the subtraction if thin clouds pass. The filters catch most of that. The rest is caught by people who have learned the look of a real mover versus noise. That judgment is why a personal blog post can contain a hey. Look at this image while the formal pipeline keeps its steady pace. A scientist might share an odd frame to invite curiosity while waiting for the official pages to fill in. That choice can be frustrating to readers, but it is not proof of anything on its own. It is a kind of thinking out loud that science has always done, only now it happens on the internet. If the rumored interstellar object really was first flagged by Atlas, the timing and the method fit. A fast mover, faint but not invisible, crosses the right part of the sky. A few short exposures pick it up as a streak or a dot that shifts by just the right amount. The software flags it. A human approves it. The positions go to the MPC. Other telescopes hop in. The orbit fit firms up. The JPL page appears. The eccentricity stays above 1. The error bars shrink. The committee assigns the badge. That is the pattern you can rely on without a press release. If any step is missing, you wait. Because sometimes a candidate fades or weather blocks follow-up. Or the first fit was tricked by noise and settles back into a normal elliptical path after a longer arc. For everyday readers, the simplest summary is that Atlas is the early warning siren and the neighborhood watch rolled into one. It points out the stranger walking down the street. The town made up of many observatories checks. The ID writes the report and files the paperwork. The courthouse FMPC and the IAU committee stamps the form. JPL adds the map with the path. Then, and only then, is the name real. In the time between the siren and the stamp, there will always be stories and guesses, charts and whispers, and now and then a blue smudge in a place you did not expect, all of which can be part of the human side of skywork, while the official trail builds in the background where the numbers live and where anyone with patience can read them as they appear and see whether the word Atlas is just a rumor or a credit line tied to a set of times and positions that will still look solid a week from now and a year from now, as the tiny dot we almost missed heads back into the dark and the survey turns to the next patch of sky and keeps scanning without fanfare, the way it was designed to do. A rover does not see the sky the way our eyes do. It sees with instruments built for work, built to be tough, and built to send useful pictures home through a very skinny radio pipe. On Mars, Perseverance uses two main kinds of cameras for views above the horizon. The navigation cameras, often called Navcams, are a matched left and right pair that look out with a wide field. They are there to help the rover drive, avoid rocks, and understand the terrain and the light. The science cameras on the mast, known as Mastcams, are a matched left and right pair with zoom. They can go wide to show the scene or tight to pull in far details. Both systems can look at the sky, but they were designed for different jobs. And that shows up in the pictures. Navcams favor reliability and speed. They usually take short exposures, so nothing blurs if the rover jiggles. Their lenses are wide, so they can see a lot at once. They use automatic exposure and automatic white balance that try to make a safe, usable picture under changing light. Those choices are perfect for driving and quick checks. They are not ideal for catching very faint points in the daytime sky. A short exposure, a wide lens, and a bright, hazy sky make small, dim things hard to see. When Navcams do catch something in the sky, it often sits close to the noise floor, where small quirks of the sensor and the software can change how a few pixels look. Mavcams behaves differently. With zoom, the team can choose a tighter field of view. That increases apparent detail and reduces how much hazy sky falls on each pixel. Mastcams also gives more control over exposure and color. It can run longer exposures when the rover is steady or use specific settings to match science goals. A mast camera can be aimed on purpose to the part of the sky the team wants. If you are trying to find a faint smudge, that control helps. Even then, the camera still fights the Martian sky. Daylight on Mars contains a lot of red dust scatter. The sky can be tan, salmon, or butterscotch, depending on dust and sun height. Closer to the sun, the sky can shift toward blue at sunset because of how fine dust particles bend light. All of that sits on top of the camera's own way of making color. Rover color starts with a mosaic, not with full-color pixels. The sensor is covered by a tiny checkerboard of color filters. Some pixels see red, some see green, some see blue. The raw sensor does not record a ready-made color picture. It records one color per pixel in that pattern. To build a normal image, software guesses the missing colors for each pixel by looking at its neighbors. That step is called demosaicing. It works very well for normal scenes. But when a faint point sits on a smooth sky, the math can create small halos or color shifts. If the point is only a few pixels wide, the guesswork around it may add a blue or green tint along one edge and a different tint on the other. That is not a trick or a cover-it, is a side effect of turning a color mosaic into a picture. Your screen can show dot compression matters too. The rover cannot send every bit home. It has to squeeze files to fit the radio link and the schedule. The most common squeeze is a form of JPEG compression. JPEG breaks an image into small blocks and turns smooth areas into simple formulas that take fewer bits to store. It is very efficient on skies and sand, but it can leave faint block edges and ringing around small bright spots. When you look at a faint object against a bright, smooth sky, compression can add a little edge that looks like a wing, a tiny shift in color, or a noisy halo. The effect is worse at high compression and shrinks when the team uses lower compression or lossless modes. But you still see it in quick-look images posted fast. White balance is another piece. Human brains are great at guessing what white should look like under any light. Cameras are not. They rely on software to decide which mix of red, green, and blue should be neutral. The rover has color targets mounted on the Deca kind of space color chart, so the team can adjust images later to match a known standard. The raw page you see on the internet may not have that correction yet. It may be auto-balanced based on the average color in the scene. In a view full of tan dust and rusty soil, the auto-balance can lean too far and make a cool area look extra blue. Or it can pull color toward gray in a way that hides faint tints. A later calibrated version may look different, not because the scene changed, but because the team used the color target and lab data to correct the file. Dust lives in two places, the air and the optics. In the air, dust makes the sky bright and soft. It lifts the background levels so small, dim things have to compete with more glow. On the optics, fine dust can stick to the protective window in front of a camera. Each tiny grain scatters light and adds a veil. That veil lowers contrast, especially near bright parts of the frame. Sometimes a dust grain or a tiny scratch makes a small soft circle called an out-of-focus mote when the lens is aimed far away. That circle is not a real object in the distance, is a shadow on the sensor from dust near the camera. It can look like a faint planet or a blur if you do not compare frames. Engineers watch for these and build flat field maps that help remove them during processing. On raw pages, you may still see them. Shutter and motion can add one more twist. If the rover is settling after a small move, or if the mast has a tiny vibration, a long exposure can smear stars into short streaks. The cameras try to avoid that by using short exposures. That choice saves sharpness but costs sensitivity. That trade is why most daytime sky frames from a rover show only the sky color and no stars. At twilight or night, the team can ask for longer exposures and catch more. But those shots are rare because long exposures conflict with driving, drilling, and many other jobs. Even at night, wind and fine dust can shake the rig just enough to blur a ... file names and storage tell their own story. Each rover image is saved with a name that encodes the sol number, the camera code, and often, which I took it. The rover stores images in local memory, bundles them into packets, and sends them up when a relay orbiter is overhead. Orbiters like Mars Reconnaissance Orbiter and MAVEN forward the data to Earth through the Deep Space Network. Ground systems unpack the packets and reconstruct the images. A quick-look copy lands on the public raw page with minimal processing. That means what you see there is fast, but not final. Later, calibrated versions go to long-term archives built for science use. Those files have better color, fixed lens artifacts, corrected vignetting, and often more accurate brightness. They arrive weeks to months later because the pipeline is careful by design, because there are two eyes for both Navcams and Mastcams. Stereo checks are possible. If a faint mark shows up in the left camera and not the right at the same time, that leans toward a sensor hit or an optical mote. If it shows up in both, with the right offset between the two views, it acts like a real feature in the scene. If the rover took a quick burst, you can also check whether the mark shifts the way a real sky object would shift as the camera or mast moves. A mote or a hot pixel sticks to the same sensor spot. A speck in the sky sticks to the same place on the sky and moves on the sensor when the camera moves. That simple logic left, right, and frame-to-frame beats guesswork every time. When you are judging a tiny blur, there are a few more small things that can fool the eye. Cosmic rays hit sensors and leave bright, sharp streaks that slice across a few pixels. They often look white and clean-edged compared to soft sky features. Lens flare can add a pale, round blob that lines up with the sun and the center of the frame. Rolling fog or dust across the lens can add a gentle gradient that makes one part of the sky look cooler or warmer. JPEG ringing can outline bright edges with a faint echo. Demosaicing can paint tiny checkerboard colors around a single bright pixel. Each of these has a fingerprint. Once you know the prints, you can look past them and keep the few pixels that matter. The ones that do not match any artifact and do match the way. The sky should behave over time. Put all of that together and you get a fair picture of how perseverance sees up. Navcams give fast, wide, practical views with auto settings that try not to be wrong. They can show a faint mark, but they are not tuned for tiny sky targets. Mastcams can zoom, hold exposure longer when safe, and capture cleaner color. But it still works through dust, compression, and a Bayer mosaic that has to be demosaiced. Raw pages show quick versions that may carry auto balance and compression quirks. Archive versions come later with careful color and fixed flats. Stereo eyes let you test left-right. Bursts let you test frame to frame. Cal targets let you fix white. Dust, scatter, and compression explain odd blues and greens in a sky that is mostly tan. And the more you learn those pieces, the easier it is to decide whether a little smudge is just the camera doing its best on a dry, bright planet or something out there, riding the air above Jezero the way of faint. Guessed would when the rover looks up and the radio pipe is thin and the team has to make every pixel count while the next pass waits and the schedule rolls. On to the next shot and the next packet. And the next careful check on the ground, where the bits are turned back into the sky you and I are trying to read together. Color can be slippery, especially when we compare pictures taken by different cameras in different places. Earlier reports called the object green. The rover frame shows a faint blue smudge. On the surface, that feels like a contradiction, but there are many ordinary reasons. A small point in the sky could swing from green to blue without anything mysterious happening. Cameras do not see color the way our eyes do. Each sensor has its own hearing range for red, green, and blue. Some blue pixels are more sensitive than others. Some green pixels overlap a little with yellow. When a point of light is just a few pixels wide, small differences in how those pixels respond can nudge the apparent color. A telescope in space using a filter that isolates a bright green band will paint the object green because that is the slice of light it recorded. A rover on Mars using a wide color setting will mix whatever light arrives with a sky that is already colored by dust. And the balance can shift the same point toward blue. White balance is another quiet driver. Our brains correct color on the fly. Cameras have to guess. A rover often uses auto white balance for quick looks, and that guess leans on the average color in the scene. On Mars, the ground is red-brown and the sky is tan. Auto white balance tends to pull the whole frame toward neutral, which can make small, cool features look more blue than they would after a careful calibration using the rover's color target. A raw page image may carry that auto setting. Later, the team can apply a labist correction that moves the whole palette back toward true. If you compare a quick-posted frame and a calibrated archive frame, the overall tone can change even though the original light was the same. The sky itself matters. Earth's daytime sky is blue because the air scatters short wavelengths more. Mars has a lot of fine dust, so the daytime sky is often butterscotch and the sunsets can look blue near the sun because the dust bends light in a special way. That background color is the canvas the object sits on. A faint green glow that would pop against a black space background can be washed out against a bright tan sky. Meanwhile, any blue light from the object or from the way the sensor reconstructs the color can stand out slightly, because the blue channel may be the cleanest path through the dust at that moment. The same object against dark space looks green. Against a dusty daylight sky, it can lean blue because the background is different and the camera had to compress the range to fit what it could send. Exposure time plays a role. Space telescopes and ground observatories often take long exposures and stack them. That lets faint emission lines very specific colors of light rise above noise. A common green in comets comes from diatomic carbon, a gas that shines strongly in a green band when sunlight excites it. Narrow filters are tuned to that band, so the image turns green by design. A rover in daytime uses short exposures so it can drive and so bright parts do not blow out. A short exposure reduces the chance of catching a faint green emission line and increases the chance that what you see is broadband reflection or a hint of the blue channel that the camera's math emphasized during demosaicing. Longer exposures on the rover could help, but they are rare during work hours, and the mast needs to be very still. Compression is the quiet artist that repaints edges. The rover squeezes images with JPEG most of the time to fit the radio link. JPEG chops an image into small blocks and simplifies smooth areas like sky. When a tiny bright spot sits in that smooth area, the math can leave a faint ring or a color fringe. Often the fringe lands in the blue channel, because the algorithm's small errors and the sensor's blue sensitivity combine in that part of the spectrum. It is not a fake feature. It is a side effect of saving space. A lossless or low compression version of the same frame can look less blue around the edges of a small point. Even though the scene did not change, demosaicing adds another nudge. The sensor has a red-green-blue checkerboard over its pixels. The camera must guess the missing colors for each pixel by looking at neighbors. When the subject is a small, soft blur on a uniform sky, the guess can create a cool fringe on one side and a warm fringe on the other. The intensity is tiny, but when we are hunting for color in a feature that is only a few pixels across, that tiny shift can sway our eyes. Some demosaicing methods favor keeping edges sharp. Others favor smooth color. The chosen method for quick-look rover images aims for speed and clarity, not scientific color. And it can make a faint point lean blue or green, depending on local contrast. Lens behavior can push color too, especially near the edge of the frame. A little chromatic, aberration, different colors focusing at slightly different distances can add a faint blue. Rim on one side of a small highlight and a faint red or green rim on the other. The rover's optics are very good, but any glass system under dust, temperature changes, and mechanical stress can show a tiny hint of that effect. If the smudge sits off-center, that edge tint can show as a blue bias even if the source light is neutral or greenish. Move the camera, and the fringe moves with it. which is one way to tell lens tint from a true emission color. The light itself can change with context. A comet or active body can glow green in narrow bands when excited gas like C2 is present. The same body can also scatter sunlight from dust, which is more neutral or slightly blue in a camera that leans toward blue when white balance pulls the tan sky back. If the object rotated between observations, a side with more dust or ice could face the camera, changing the reflected color. If a jet turned on or off, the mix of emission and reflection shifts again. That means a green object in a long, filtered exposure taken from Earth or a spacecraft can appear as a blue-leaning smudge in a short broadband. Daylight frame from Mars if the emissions are weak at that moment, and the reflection is what the camera catches. Distance and background. Density also matter. If the object was closer during earlier observations, the emission might have been stronger. If it was farther or in a dustier air column during the rover shot, the green emission could be suppressed and the camera might pick up a cleaner signal in the blue channel, where the sky was less bright after balancing. The angle to the sun changes contrast as well. At high phase angles, forward scattering dust can brighten the background and wash out certain colors more than others. At low phase angles, the surface can reflect differently, favoring shorter wavelengths in some materials. A few smaller effects can add up. Sensor noise is often higher in the blue channel, and the camera's noise reduction might smooth red and green more aggressively, leaving a slightly cooler look for a tiny feature. A mild veiling glare caused by dust on the protective window or by internal reflections can lower contrast and make warm tones drift toward gray, letting cooler tints peek through. A slight misfocus, perfectly fine for horizon work, can spread a small source over more pixels and let demosaicing and compression shape the color more than the source does. All of these reasons stand before we even lean on the simplest one. Different instruments were used. A telescope image that appears green may have been taken through a filter designed to show that green emission and nothing else. A rover image that appears blue may have been auto-balanced in a tan sky with short exposure and JPEG compression, while demosaicing and a tiny lens fringe gave a faint cool cast to a few pixels. If the object also changed, rotating, venting, or moving into a different background, the color mix in the sensor shifted again. None of that requires a special event. It is how cameras, light, and dusty skies work when you push them to show the faintest things they can show in the middle of a long workday on another planet where the pipeline has to favor safety and bandwidth before it gets around to careful color, and where a small smudge can switch sides between green and blue depending on which tool looked, which slice of light it chose, how long it stared, and how much math it had to do to send a few precious pixels home. First, we ask a simple question. Is the blue smudge a thing in the sky, or is it something inside the camera? That means we compare what we see with the most common glitches a rover camera can make. Each glitch has a look and a behavior. If the smudge looks and behaves like one of them, we stop chasing it. If it does not, we keep it on the table and test it harder. Start with cosmic ray hits. Space is full of high-energy particles. When one slams into a camera sensor, it can leave a bright, sharp mark on a single frame. These hits are often skinny and crisp, like a tiny white scratch or a needle-thin streak. They can also be a small, squarish spark that looks too clean compared to natural blur. The giveaway is that they appear in one frame and vanish in the next, even if the camera has not moved. They also appear in only one eye if you have a left and right camera shooting at the same time, because the particle strikes only one sensor. If our smudge is soft, a little feathered, and shows up across two eyes with a small stereo offset, it is not acting like a cosmic ray. If it repeats in two frames taken a second apart, it is not acting like a cosmic ray. Cosmic rays are jump scares. This smudge looks more like a soft whisper, Now think about hot pixels. These are single pixels or small clusters on a sensor that gets stuck on. They show up as tiny bright dots, often pure white or a very pure color, in the exact same pixel location over and over. You can find them by looking at several frames from the same camera. The dot sits on the same XY spot while the scene behind it changes. They do not move with the sky. They do not care where the lens points. A hot pixel also has clean square edges at the pixel level. It does not look like a natural blur. If the smudge moves across the sensor when the camera nudges or when the mast settles, that motion already argues against a hot pixel. If the smudge is in a different place in the left eye than in the right eye, with the right stereo separation, it is not a single bad pixel. Hot pixels do not parallax. Rolling shutter, smear, and readout trails come next. Some camera sensors read out the image one row at a time. A very bright source can bleed along the readout direction, leaving a faint vertical or horizontal line from the bright spot. You also see smear if the camera moves during exposure or if the mount vibrates. Stars turn to short streaks, and bright edges pull a faint tail. The angle of the streak usually lines up with either the readout direction or the shake direction, not at a random angle. The smear tends to be straight, not oval. If our smudge is an isolated oval patch, not a line, and if no bright object sits at the end of a trail, it does not fit readout smear. If the blur's angle changes when the camera angle changes, that can be motion. But if the blur holds the same soft oval shape, no matter the mast's tiny settling, it is not behaving like a shake streak either. Dust motes on the optics are a classic trap. A mote sitting on or near the sensor shows up as a soft, donut-shaped shadow when the lens is focused far away. It often has a darker ring and a lighter center. It is out of focus because the dust is close to the sensor, not out in the scene. The key test: the donut stays stuck to the same pixel coordinates when the camera pans a little. The sky and the horizon slide under it. The donut does not budge. If the focus or aperture changed, the donut size can change, but its position does not move with the scenery. That is the opposite of a real sky feature, which stays in the same place in the sky, coordinates, and moves across the sensor when you tilt or pan. So we watch what happens in a tiny tilt between frames, or we compare left and right eyes. If the smudge rides with the sky and shows stereo offset, it is not a censored dust donut. Lens flare is another suspect. Internal reflections between lens elements can create soft orbs and streaks when a bright light sits near the frame, especially close to the sun. Flare artifacts often line up along a straight line between the bright light and the center of the image. You can see a family of ghosts, one big orb, one small, sometimes a rainbow tint, and sometimes a thin streak. They change shape and position as you shift the camera angle a little, and they get stronger when the bright source approaches the frame. The color can lean green because of coatings, which fools people into thinking green object. The test is simple. Check the sun direction. Look for a line from the sun through the frame center, and see if the smudge sits on that line with other faint ghosts. If the sun is nowhere near the line, or if there are no sibling ghosts, and if the smudge does not jump when the camera angle changes a few degrees, that argues against lens flare. Compression halos and demosaicing fringes are subtle but common. JPEG compression chops an image into small blocks and can add faint ringing around a small bright mark on a smooth background. Demosaicing, the math that rebuilds color from the sensor's red-green-blue checkerboard, can create tiny color fringes around a single bright pixel or tiny blur. These effects tend to wrap close around edges, often with a thin blue or magenta halo. They usually hug the bright spot and look symmetrical. One way to test this is to compare a higher quality version of the same frame available, or to zoom in and look for the block grid. If the halo follows an 8-8 block pattern or has a checker texture, it is compression. If the color fringe flips on opposite sides of the mark, it is the demosaic. If the smudge holds its shape and softness across versions and does not break into block edges, it has a better chance of being a real faint source. There is also shutter smear's cousin, blooming or charge bleed in very bright pixels. This happens when a sensor well overfills and spills charge into neighbors, producing vertical or horizontal tails. It needs a very bright source and usually happens near the sun or a specular glint. The tails have hard edges along rows or columns. A small low-contrast oval on a bright sky is not the usual face of blooming. If the frame has no bright glint and the mark is soft and low, blooming is a weak match. A good habit is to build a little evidence table in your head. Does it show up in both eyes of the rover at the same time? If yes, that hurts cosmic ray and hot pixel theories. Does it land at the same pixel in multiple frames, even as the camera shifts a hair? If yes, that helps the dust mode idea. If no, that hurts it. Does it line up with the sun-to-center line and travel with other flare ghosts? If yes, that helps lens flare. If no, that hurts it. Is it a line or a soft oval? A line favors smear. An oval favors an object or a defocus artifact. Does a higher quality or lower compression copy keep the mark, or does it change shape into blocks? If it keeps the mark, that hurts the compressionly idea. With just a few practical checks, the field of suspects shrinks fast. You can also check the color behavior. A cosmic ray hit is usually pure white or a very pure color and does not feather into the sky. A dust mote is neutral in color and looks like a gray donut, not a blue-leaning haze. Lens flare orbs can be greenish, but they tend to come in families and move with camera angle. Compression halos create a thin-colored ring hugging the edge. They do not create an isolated, free-floating oval. If our smudge is a faint blue patch without a sharp rim, away from the sunline, repeating across left and right eyes with stereo offset, and present in 2 nearby frames as the rover rocks, the odds move away from glitch and towards something small in the sky. Another useful check is to measure its pixel coordinates and compare them to a fixed reference on the image, say, a distinctive notch on the horizon. If the smudge's offset from that notch changes between frames when the camera tilts, it is tied to the sky, not the sensor window. If you can find a rough star position in a twilight frame and the smudge shares the same drift, that is stronger still. In daytime, you may not see stars, but you can still follow how the camera's tiny motion moves the smudge relative to the frame. Finally, remember that real faint sources tend to act the same way across both eyes and across time, even when everything else changes a little. Artifacts tend to act the same way across very different scenes because they live on the sensor. Repeat the left-right test. Repeat the next previous frame test. Note the sun angle and check for ghosts. Zoom way in and look for block edges or checker halos. Watch how it behaves when the horizon rises a few pixels between 2 shots. If it sticks to the world, it is a mote. If it sticks to a row, it is smear. If it sticks to a single frame, it is a cosmic ray. If it sticks to a story across eyes and moments, then it is fair to carry it forward to timing and geometry. Because that is where we ask the next question: does this small, steady smudgeland where the math says a fast visitor should be at that moment, from that place, under that sky, with that camera quietly doing its job while the rest of the world argues about words on a web page and the little blue mark just sits there, waiting to be checked the way we check all small things that might matter more than they look. When people say the object is on a 5-degree plane, they are talking about inclination, which is just the tilt of an orbit compared to the flat sheet of the solar system. The easiest way to picture it is to imagine the planets riding around the sun on a giant dinner plate. That plate is the ecliptic plane. Most of the big bodies circle close to the surface of that plate. Inclination tells you how much a path is tilted up or down from that surface. 0 degrees means the object moves right on the plate. 5 degrees means it is skimming just a little above or below it, like a paper airplane flying over the plate at a gentle angle. 5 degrees sounds precise, and it is a small number. In everyday terms, it is a shallow tilt, about the slope of a long driveway. At the distance of Earth from the Sun, a 5-degree tilt means the object sits roughly 1/10 of an astronomical unit above or below the ecliptic when it crosses our longitude. 1/10 of an astronomical unit is about 9 million miles, which is big in human terms but small compared to the width of the solar system. Many asteroids and comets, we already know, run at small tilts. Mars itself travels on a path tilted by less than 2 degrees relative to Earth's orbital plane. So a 5-degree claim is not wild on its face. Says the object is moving in a band where our searches spend most of their time. Looking anyway. The reason you hear this number at all is that our surveys are built to find motion in that band. Search programs like Atlas, Pinesta, ROS, and others spend a lot of hours scanning near the ecliptic because that is where most near-Earth asteroids live. That creates a built-in bias. We catch more things that pass near the plate than things that streak far above or below it because we simply don't stare up there as often. So if an interstellar object shows a small inclination, part of that may be because it really came in near the plane. And part may be because that is where our nets are hanging. The sky is big. Time is short. We fish where the fish usually swim. There is also a second reason low inclinations show up. The sun is moving through the local sea of stars and gas, and our gravity focuses passing debris toward the ecliptic region more than toward the poles of the solar system. Think of it like rain hitting a windshield. The airflow pushes more drops to certain paths. Over long times, that can bend the traffic of passing rocks and ices so that we see more of them near the plane where our planets orbit. So a small tilt is not proof of anything special by itself. It is possible, and it is a little unusual. If you expected a truly random arrival from any direction, but it is not shocking. What would make 5 degrees more than a rumor is a proper orbit fit, and that needs more than one night of dots. The path of any moving object in the sky is first seen as a straight line across the starfield. That is only the 2D picture. 2. Turn that line into a 3D path. You need distance, and to get distance, you need time. Observers take positions against background stars over several nights. The change in angle as Earth or Mars moves gives the parallax you need to estimate how far away the object is. With distance and direction, you can work out a full orbit and calculate inclination with an error bar attached. With just one night, you can guess. With 2 or 3 nights, you can start to be confident. With a week, you can write down a number and defend it. This is where a Mars plus Earth view would be powerful. If both planets spot the same object within a few days, their wide separation acts like a giant set of binoculars. That big baseline lets you triangulate distance quickly. Once you have distance nailed down, the tilt relative to the ecliptic drops out of the math pretty cleanly. But even then, you need care. The coordinate systems on Earth and Mars must be lined up to the same star catalog. The times must be accurate, and the instruments pointing must be well calibrated. A small time error becomes a big position error at interstellar speeds. A small pointing bias becomes a wrong tilt. That is why astronomers keep talking about multiple nights of positions. They want the errors to average out. Another trap is mixing what you see on a picture with what the orbit really is. A line across the sky at a shallow angle is not the same as a small orbital inclination. The path you see is a projection on the dome of the sky. If the object is close, that projection can be steep even if the real orbit tilt is small. If the object is far, the projection can be shallow even if the real tilt is large. Without distance, the sky track can fool you. So when someone says they eyeballed 5 degrees from one image, take a breath. That is not how it is measured. Astronomers fit a full 3D path to many dots and report the inclination from that path with an uncertainty number, not from the tilt seen in a single frame. Outgassing and non-gravitational pushes add another wrinkle. If a small object is venting gas, sunlight, or jets can give it a gentle shove. That can curve the path, and if you do not account for that extra push in the orbit fit, it can bias your inclination. The curve may look like tilt when it is actually a sideways push. For Oumuamua, teams added a small non-gravitational term to get a better fit. The same care would be needed here before trusting a 5-degree claim to 3 decimal places. You want to know whether the tilt is real geometry or an effect of a weak jet tugging the object a bit off a pure gravity line. If the 5-degree number does hold after a proper fit, what would it mean? It would say the object is moving in a plane close to the one where most of our planets live. That could simply be the path the object had when it wandered into the sun's reach. It could also hint that the object was once part of a disk around another star, the way our comets and asteroids formed in a disk long ago. Disks launch debris mostly near their own plane. If many interstellar visitors we see arrive with small inclinations, it might mean we are sampling the flat leftovers of many other disks, not random chunks from all directions. If, over time, we see a mix, some with small tilts, some with big ones, that would argue for a more varied origin story. We should also compare to the first 2 visitors. Oumuamua's inclination relative to the ecliptic was not extreme. Borisov's was modest too. Both moved in ways that did not scream coming from the poles. That fits the idea that our view is biased toward the plane and that gravity funnels traffic that way. So a 5-degree claim for a third visitor would sit in line with what little we already know. It would be a little unusual only if you expected interstellar roads to be evenly filled in all directions. The data so far says our roads see more cars near the plate. From a practical viewpoint, a low inclination is helpful. It keeps the object in survey fields longer. It lets follow-up telescopes track it more easily without jumping between far-separated sky strips. It keeps the phase angles friendlier for brightness. It even helps with cross-checks from Mars, because the Martian orbital plane is also close to the ecliptic. Geometrically, everything lines up better when the tilt is small, and that can speed up confirmation to move from rumor to result. Here is what the observers will do. They will gather sky positions from as many nights as possible, ideally from more than one hemisphere, and, if the geometry allows, from Mars as well. They will fit a hyperbolic path if the object is truly interstellar. And they will include a small non-gravitational term if the residuals demand it. From that fit, they will report inclination with an uncertainty, like 5.2 plus or minus 0.6. The Minor Planet Center will post the measurements. The JPL small body page will show the orbit elements. Other teams will refit the data and see if they agree. After a few days of this, the number will either hold steady or drift. If it holds, the 5-degree claim becomes a real property, not a headline. If it drifts, then the early talk was simply the feeling we all get when we try to read the sky. From too few dots too fast, and the steady work of adding nights and shrinking errors did what it always does, turn a guess into a measurement that can live on a page without needing a shout to make it feel true. When people started repeating the claim that the object rides on a 5-degree plane, what they really meant was that its path has a small tilt to the flat sheet of our solar system. Picture the planets moving on a giant dinner plate around the sun. That plate is the ecliptic. Inclination is simply how much a traveler's path tilts above or below that plate. 0 means it is skimming the surface. 5 degrees means just a gentle rise, like the slope of a long driveway. In space, even small angles stretch into big distances. But 5 degrees is still a shallow path compared with wild, over-thieved top tilts. A number like that is possible, and it would not be shocking by itself. Many asteroids and comets we already know live close to the plate. And several famous visits from beyond have not arrived from extreme angles either. What makes a number like 5 degrees feel unusual is the story people wanted to tell. They hear a small tilt and start to imagine intention or alignment. The truth is simpler. Most of our surveys stare near the ecliptic because that's where the planets and near-Earth objects are. We fish where the fish usually swim. We also benefit from a mild focusing effect of the sun's gravity and the way our system moves through local space, both of which can guide passing debris toward the plane over long times. So a low inclination is not a secret code. It is a small clue that needs careful math to become anything solid. Math is how a rumor turns real. The path drawn on a single picture is only the 2D shadow of a 3D motion. You get a clean inclination only after many dots on many nights are turned into a full orbit. Observers across longitudes measure the object's position against background stars night after night. The slow change in viewing angle as Earth moves gives distance through parallax. With distance and direction, you can fit a 3D path and then read out the tilt with an error bar. If you only have one night, you are guessing. With 2 or 3 nights, you start to pin it down. With a week, you are in business. Add Mars to the mix and the solution comes faster. If Earth and Mars both see the same object, their wide separation acts like a giant pair of eyes. The baseline between worlds makes parallax strong, distance falls out quickly, and the tilt relative to the solar system's plane becomes a number you can defend. Even then, you have to be careful. Small timing mistakes grow into big position errors for fast movers. Small pointing biases shift the tilt. If there is any gentle jetting from the body that pushes it off pure gravity, that needs to be folded into the orbit fit, or you will read a curve in the path as if it were a permanent tilt. That is why astronomers keep saying we need multiple nights of positions. It is not stubbornness. It is how you swap the feeling of 5 degrees for the measurement of 5 degrees plus or minus a fraction soon after the tilt talk. Another word started to circulate: nickel. People said the object might be nickel. That sounds bold, like we suddenly know what the rock is made of from a single faint picture. That is not how composition works. Nickel is not read from a color thumbnail. It is inferred from a few real tools that each have limits. If a target is close enough to bounce radar off, you can measure how bright the echo is. Metallic surfaces reflect radio waves very well, so their radar albedo is high. But radar works only when the body is close, and a Mars sky snapshot does not give you that. Another way is to spread the light into a spectrum and look for features that match certain minerals and metals. That takes stable, calibrated spectroscopy and a decent signal-to-noise. Reflectance curves can hint at iron and nickel through their overall slope and certain broad absorptions. They do not stamp Nephi percentages on the screen. A third path is indirect, if small fragments fall into Earth's atmosphere and are recovered as meteorites. Lab tests can show nickel abundances. But that's not what's happening here. If nickel is real for this object, many observers should be able to point to the same spectral shape or radar behavior. A rover daytime frame cannot do that alone. It can suggest a color that makes people curious, but the claim stands only when independent spectra agree. When polarimetry and thermal data line up, and when the story repeats at more than one wavelength. Until then, nickel-Rick is a placeholder for a question, not an answer. The next term that turns heads is a sunward jet. The idea is that the object gives off a small push, not explained by gravity alone. That push can come from gas or dust puffing off the warm side that faces the sun. The jet acts like a tiny thruster. The result is a drift that does not match the path gravity predicts. It sounds like science fiction, but we have seen gentle non-gravitational acceleration before. Oumuamua showed a mild version. Teams fit the data and found that the object behaved as if it had a small outward pressure, perhaps from solar radiation on a large area or from slow venting of gas that we could not see as a normal coma. The physics behind a little push is not impossible. It is rare and easy to overstate. Small outgassing can be seasonally on or off as the body rotates and warms. Thermal lag can shift when jets fire, like the Yarkovsky effect for sunlight heating. If you do not include a small jet term in the orbit model, the path will not fit perfectly, and you might be tempted to call the leftover impossible. That is not helpful. The right way is to add one small, realistic, non-gravitational term to the fit. See if it improves the residuals, and then ask if more than one team measures the same push with the same direction and similar size. If they do, the jet is a measured property, not a rumor word, because we all remember Aumuwa. It is natural to build a bridge between that story and this one. People also bring up IM-1, the 2014 fireball that some officials later said was likely interstellar based on its speed before it hit Earth's atmosphere. You can hear a pattern forming in the way people talk. They mention non-gravitational acceleration, unusual spectra, odd shapes, and then they let the pattern do more work than it should. Patterns help us build a checklist. They do not certify a match. The checklist looks like this. Does the new object show a small drift that fits a simple jet model when more than one group measures it? Does the light curve support a stable spin period and a shape that can explain the brightness swings? Do spectra from different observers agree about any strange chemistry? Do the orbit fits agree that the path is truly interstellar with a strong hyperbolic signature? If enough boxes fill, the new case echoes the earlier ones in ways that matter. If only one or two boxes fill, the echo is just a sound our minds make when the facts are still thin. A careful checklist keeps us honest, because it asks for measurements that repeat across teams and tools before we start treating a family resemblance as if it were proof of blood, one of the best. Ways to jump from thin to thick evidence is to see the object from two worlds at once. Triangulation with a Mars plus Earth baseline is powerful and fast. The math is high school trigonometry, dressed up for space. You take the right ascension and declination of the object as seen from Earth at a precise time. You take the same kind of position from Mars at the same or a carefully corrected time. Because the two planets are far apart, the line of sight from Earth and the line of sight from Mars cross at a sharp angle. Where they cross gives you the distance. With distance known, the 3D velocity follows when you add how the position changes over a day or two. With 3D position and velocity, you can tell if the path is bound or open, if the inclination is small or large, and if a small non-gravitational term is needed to satisfy all the measurements. The big hurdles are not the equations. They are the details. Both sides have to use the same star catalog so their sky coordinates match. Both sides need precise timestamps. Both sides must account for light time delay. The fact that you are seeing where the object was minutes ago, not where it is now. When those chores are done, the result can come quickly. And a story can go from maybe too likely in a few days, while the measuring unfolds. A paper trail grows in familiar places. That trail is the most honest part of any discovery. You do not need a press release to trust it, and you do not need social media to find it. It starts with the Minor Planet Center's confirmation page, where new fast movers are listed by provisional codes and early positions. It continues with observation logs submitted by surveys and individual observers with accurate times and sky coordinates. It shows up in Minor Planet electronic circulars when the case is strong enough to share widely. It appears on the JPL Small Body Database as an orbit page with elements and uncertainties that update as more positions arrive. If Mars is involved, the raw image servers and long-term archives like the Planetary Data System eventually add files with product IDs, times, and instrument names. University observatories might post quick notes. Professional astronomers post short preprints on open servers for early review. If the event is real, this trail grows within days, sometimes hours, and each step links back to the one before. If days pass and the trail is still thin, or if parts of it are missing where they should be, that is a sign to wait, not a sign of conspiracy. A trail this many people rely on does not depend on one person's mood or one organization's feed. It lives in shared pages that do not go dark when the public voice is quiet. That brings us to why a scientist might post an early image on a personal blog in the first place. Some people read that choice as a signal that someone is trying to hide or bend the story. Often, it is simpler. The preprint culture in science encourages early sharing of ideas and draft results for feedback. A personal blog is an easy place to say, "Here's something interesting. Can others check this?" A blog post does not replace a formal archive or a paper. It is a way to invite eyes while the slow work of checking, calibrating, and submitting moves forward. During a government shutdown or any pause in public affairs work, the official channels cannot publish even small notes, while many individual scientists can still speak for themselves. That split creates moments where a personal blog is the first place you see a frame that later lands in a proper archive. The smart move is to treat a blog like a doorbell, not a verdict. You acknowledge the knock. Then you walk to the records that matter and see what shows up. There in the days that follow, people also ask whether Mars orbiters like Mr. O or TGO could have seen a fast visitor and why any try would take days to turn into a clean picture. The orbiters have tools that can look up, but those tools are built for other jobs. The Mars Reconnaissance Orbiter carries hierarchy, which can take very sharp images of the surface with a narrow field of view, and CTX and Marcy for context and weather. ESA's Trace Gas Orbiter carries Casillas for color images and instruments to study gases. In principle, any of these could try to capture a bright point in the sky if it passed through their field of view at the right time. In practice, the schedule is packed. Pointing is planned days ahead. The instruments are tuned for surface or atmosphere, and the risk of slewing fast is weighed against safety and science priorities. If a try happened, the raw frames would still need to get downlinked, checked for errors, calibrated for instrument quirks, and posted to an archive. That pipeline takes time even when the press office is active, and more time when public work is paused. So a gap between a rumor of a look and a posted, clean image is normal. The absence of a next-day picture does not tell you the try did not happen or that someone is hiding it. It tells you we are watching a careful machine do its careful steps. If you want quick ways to knock down a false story, here are a few checks that work fast and do not require special tools. The first is the background. Does the star pattern behind the object match the time and the place? Even in a daytime Mars sky, you can sometimes see a bright star at twilight or match the curve of the horizon to the rover's known view. If the stars or the sun angle are wrong, you can stop. The second is a left-right or frame-to-frame check. If the mark is a hot pixel or dust mode, it will stick to the same pixel location even as the camera moves a little. If it is in the sky, it will move with the sky. The third is the community. Within 48 to 72 hours, skilled amateurs and professional surveys will try to confirm any big claim. If no one sees anything at the right place and time, that silence is a sign to pause. Not every non-detection means the thing is not there. Weather, moonlight, and geometry can hide real objects. But a full weekend of nothing from good eyes is the kind of negative result that carries weight. On the flip side, there are a few things that make a case stronger quickly. Repeated detections at the correct spot and time by more than one observer are the heartbeat. A listing on the Minor Planet Center with multiple nights and many observers is a strong sign. A JPL orbit page with a hyperbolic eccentricity above 1 and shrinking uncertainties is better still. If more than one team measures a small non-gravitational push in the same direction and range after they include it in their orbit fits, the story becomes very interesting. If a Mars observation and an Earth observation line up in a triangulation that matches the fitted orbit, you are looking at a mature result, not a rumor. None of this requires a dramatic headline. It requires people who love small numbers to agree on the same small numbers. It is worth saying that even if the smudge turns out to be nothing more than a camera quirk or a dust mote, the process still has value. Each time we check a claim like this, we teach ourselves again how to separate a story from a record. We get better at reading raw images, at using left-right checks, and at understanding white balance, demosaicing, compression halos, lens flare, and dust. We learn to search the Minor Planet Center page and the JPL small body database and to read the dates and the codes there. We grow more comfortable with waiting a day or two for independent confirmation. That patience does not kill curiosity. It protects it. It keeps the mind calm enough to accept a real surprise when it arrives and to let a false alarm fade without anger. The sky is generous with lessons if we let time do its part. A small blue mark that taught you to ask for 2 frames and a stereo check has already given you something you can use forever. A weekend where you watched the confirmation page refresh and saw other people looking when you looked has already pulled you closer to the real way discoveries are made. Whether the next line added to the list of interstellar visitors shows up this week or not, the habit you just practiced will still be the right way to meet it. With clear eyes, slow breathing, and the simple tools that carry you from I saw a color to we measured a path. From an angle guessed on a picture, to an inclination written with an uncertainty, from a word like nickel said in a comment to a spectrum posted with a legend and a file you can download and check, and from a rumor heard at midnight to a record you can point to 3 months from. Now when someone else asks the same questions you asked tonight, Chapter 20. If this really is what it appears to be on Interstellar, visitor caught from the surface of another world, then we have reached a quiet turning point. Not because a single blue smudge can carry the weight of discovery by itself, but because of what happens next if the paper trail grows the way it should. A sighting from Mars matched with a sighting from Earth would be the first time humanity measured a traveler between the stars with a true 12-world baseline on purpose. That alone would sharpen our tools. It would give us a clean distance faster, a truer speed sooner, and an orbital tilt that is a number, not a guess. It would turn parallax from a textbook picture into a working habit, so the next time a visitor slides in, the steps are already known and practiced. It would also change how we plan. Right now, surveys watch the ecliptic band most of the time because that is where our local traffic lives. If this case holds, observatories will rehearse interstellar mode the way hospitals rehearse a drill. That means pre-built scripts, priority handoffs, and automatic alerts that move from a wide-field telescope to follow-up instruments without a long email chain. It means the Deep Space Network reserving tiny express slots for quick orbit updates. It means Mars teams and Earth teams agreeing in advance on where to point and when to hand off. So we do not lose the first days trying to line up clocks and star catalogs. The work is the same, but the tempo is different. Practice makes that tempo calm. A confirmed detection from 2 worlds would push us past the habit of treating a visitor as an on-off. It would turn a headline into a data stream, with a nail down. Distance and velocity, we would not just say interstellar in a caption. We would quantify what that means. We could test whether a small non-gravitational push is present by letting more than one group fit a jet term and seeing if the size and direction agree. We could test whether the object reflects light like metallic material or like dusty ice. By comparing spectra from different sites, not by staring at color in a compressed frame. We could drop the word impossible and replace it with numbers good enough to argue about. You would see our archives grow up a bit too. This kind of event would pressure every data system to move faster without breaking trust. The minor Planet Center would still do what it does, but more telescopes would feed it in near real time. The JPL orbit pages would update with tighter uncertainties in hours, not days, during the critical first week. Mars archives would pre-label likely sky frames so scientists can find them without wading through thousands of surface shots. Raw pages would still be honest, but the path from raw to calibrated would be shorter because the pipeline had a lane set aside for fast track during an interstellar alert. None of this requires drama. It requires the boring things to be in better order than they were yesterday. If this is real, it would also widen the circle in a practical way. Skilled amateurs already help confirm most new objects. The La2 planet. Event citizen observers would have clear, simple targets and times that matter. A small scope in Arizona or Andalusia could catch the dot that tightens the orbit. A backyard spectrograph could add the extra point that tips a reflectance curve toward or away from a nickel hint. The public would not be asked to react to a rumor. They would be invited to measure alongside the professionals, using open instructions and simple checklists. Aim here, start at this time, expose for this long. Post your positions here. That kind of shared work turns a story into a project. It also cools the temperature online, because the fastest way to lower panic is to give people something grounded to do. Mission ideas would shift. We already talk about interceptor missions that sit ready to launch when a special target appears. A confirmed cross-planet measurement would tighten the launch window and show whether a fast flyby is feasible. We would start to test small satellites that can ride along with Mars orbiters and look up on a few hours' notice without risking the main instruments. We would consider placing a simple, dedicated sky camera on the Moon or on Phobos to add a third eye that is always dark, always steady, and always free from weather. None of these ideas are expensive compared to the big missions we already run. They are small tools we would own because the problem is now defined clearly enough to solve. Science would get better in the patient way that feels slow in the moment and obvious later. With 3 interstellar points on the board, Oumuamua, Borisov, and a new 3-eye, we could begin to talk about a distribution, not a pair of anecdotes. Do visitors come with small tilts more often than big ones? Do they show weak jets half the time or only rarely? Do their surfaces look baked and dark or fresh and bright? Do spectra hint at more nickel than our local comets carry? Or is that a red herring we can let go? We would still be at the start of the story, but a start with 3 points is very different than a start with 1 and a maybe. Trends appear as lines instead of dots. Arguments settle with measurements instead of mood. There would be a social shift too. A real result that grew in public view, MPC entries, orbit fits, raw archives. Independent spectra would be a small but necessary win for open science. It would remind everyone that a government pause can turn off a press office, but it cannot dim the shared pages where the work lives. It would reward the people who waited for the paper trail, who checked left-right frames instead of screenshots, who asked for product IDs instead of adjectives. It would also reward the people who shared early with care, who said, "This is interesting. Can you check instead of this? Changes everything." That culture is worth feeding, because it is the only way to stay curious without being jerked around by hype. If you care about sleep, there is something gentle here for you as well. A confirmed calm result reduces the need to chase every rumor at midnight. When the path from alert to archive to orbit fit is practiced, we can look once, see where the next real update will land, and step away. You do not need to keep scrolling. You can set a quiet timer for the morning and trust the process to do the slow work while you rest. That is not a small thing. It is how we keep wonder from becoming worry. And if this is not relift the smudge, fades, and the trail stays thin. The work we did together still matters. We just practiced the moves we will need when the next one is real. We learned the difference between a rumor and a record. We cleaned up our own habits so we can meet the next event with less noise and more signal. The sky will give us another chance. It always does, so here is how we'll move forward together. We will keep watching the places that matter. The Minor Planet Center for new notices. The JPL's small body database for orbit fits. The raw archives for any Mars frames that enter the record, and the independent observatories for spectra and follow-ups. When a page changes, we will explain it in plain language. When a claim does not appear in those places, we will let it sit without feeding it. If this holds, we will walk you through the first confirmed interstellar object seen from another world and what that means for the next decade of skywatching. If it doesn't, we will file this as a lesson, not a loss. If this journey helped you breathe easier while still feeding your curiosity, stay with us. Tap subscribe so you don't miss the quiet, real updates. Leave a calm note about where you started to drift off or where a detail clicked for you. We read every one. And when you are ready, let the screen dim, let the room get still, and let the deep, careful work continue while you rest. We will be here with the next measured step.